Hi folks, welcome back to Physics with Captain Rod. This is video 2 here of a two-part series on introducing mechanical vibrations. So in my previous video I discussed this problem where we've got this spring of spring constant K and this mass M, this spring system. Somebody has compressed it a distance a from equilibrium and released it. We talked a little bit about how to write the equations of motion that describe the system, using either Newton's second law or principles of work and energy. And we ended up with this. d squared x dt squared plus k over m times x equals 0. And this video is going to be about how do we get from this to our solution and our period, the period of motion. Right? Well, this equation is second order, and it has a general solution that looks something like this. A sine omega t plus c cosine omega t. Now, if you watched my previous videos on solving equations of this nature, I had written this as a sine of bx in our previous example plus c cosine of bx. Let me talk a little bit about why I changed it from a b to an omega. Because if you look at this term, if you're going to take the sine of something, the something has to be in units of radians. So that means this constant, whatever it is, has units of radians per second. Okay? That's called your angular frequency. Kind of similar to angular velocity, but it's not. It's not there's nothing rotating in this problem. But because that thing has units similar to an angular velocity here, that's why I usually change that variable to an omega. All right, so anyway, moving along. Whenever you get a chance to try to whittle this equation down, you should do so. So if we look here at our initial conditions here, when time is 0, x is equal to minus a, but it's also not moving yet. So at t equals 0, our velocity, which is dx dt, is equal to 0. So I'll go ahead and write that out, all right? So dx dt equals, now when we differentiate that first term, a omega cosine omega t, I never leave myself enough room. Whoops. I'm just going to take this whole thing and move it. Okay. Now when we differentiate the next term, that's this term, we're going to get minus c omega sine of omega t, right? Because the derivative of cosine is minus sine. And this is 0 when the times are 0. So we get a omega times 1 minus 0 equals 0, because the sine of 0 is 0. So if you stare at this equation, you would hopefully come to the conclusion that a must be 0. So what that means is, in our general solution, we just lop that whole term off, and we keep the c cosine omega t term. All right. Keeping some room here. All right, now we can either apply the condition that at t equals 0, x is minus a, or we can sub into our differential equation. I guess I'll do that. All right, so dx dt is minus c omega sine omega t. All right, that's from differentiation of this term. Then if we hit it with another derivative, d squared x dt squared, we're going to get minus c omega squared cosine of omega t, right? Because the derivative of sine is cosine. And then we rewrite our differential equation as minus c omega squared cosine omega t, right? That's the second derivative term, plus k over m times x, but our x is equal to this, c cosine omega t equals 0. Now this can be factored. You can factor a c and a cosine omega t out. And then you're left with minus omega squared plus k over m equals 0. So the omega, the angular frequency, is square root k over m. I'm just going to store this up here. And I sometimes like to write it just omega squared equals k over m instead of omega equals square root of k over m, because I think that looks more aesthetically pleasing is all. All right, and we move on. We need more room. The very last thing to do is we'll apply the last condition, that when t is equal to 0, x is equal to minus a. Whoops, and I erased our solution. We had x equals, what did we have there? A, B, I think it was b cosine omega t. No, I had a c there. That's what I had there. Yeah. Suffice to say it's some constant. It doesn't matter what it is. All right. So when time is 0, x is minus a. Whatever a is some number. And the cosine of 0 is 1. So c is equal to, minus a. So the final function is x equals minus a cosine of omega t, but the omega was root k over m. And then again, the a is, in theory, is some number. And the root k over m is also some number. And this is this function right here. Now, to get the period. To understand how to get the period, you have to understand a little bit about mathematically how things work. Well, for starters, my picture is slightly off, right? At t equals 0, x is minus a. So actually, when I sketched this, and I did so before I started thinking about the initial conditions and all that, it actually is an upside down cosine wave. There we go, good enough. Yeah. At t equals 0, x is minus a. Now everything else still holds true. Now on our graph, here's a very important math thing to understand. That this distance on the graph is the period. And the cosine function cycles through 2 pi for one complete period. That means that this, the entire thing circled, has went from 0 to 2 pi. So that means root k over m times the period is equal to 2 pi. So the period is 2 pi root m over k. Okay. And the very last thing for mechanical vibrations that somebody might ask you is, what about the frequency? Well, the frequency is just the 1 over the period. I'm not even going to bother with the math about that. I will discuss a little bit about the, kind of what affecting what here. So the period is the time to complete one cycle. You'll notice that that increases with the mass. So if this is a larger mass, it means it's going to take longer to complete one cycle, and it will hence have a lower frequency. However, if you increase the K value, that means a stiffer spring. That drives the period down, which gives you a higher frequency. So anyway, this was just meant to be introductory video number 2 for mechanical vibrations. I hope that you enjoyed it. Have a nice day.